So I noticed this proposition bet on a craps table called bonus craps. And basically, the way it works is if you can roll all of the numbers less than 7 before rolling a 7, they pay you 30 to 1. Or if you can roll all the numbers greater than 7 before you roll a 7, they pay you 30 to 1. And if you can roll every number besides a 7 before you roll a 7, they pay you 150 to 1. And because this is in the middle of the table with the hard bets and things like that, I figured that the odds must be tremendously in the house's favor, but I didn't have an idea immediately how to figure out how much they were in the house's favor. So I went to my usual go-to for such things, which is the Wizard of Oz, and I looked up this bonus craps. And Mike says that the probability of winning is about 2.5%. And what got my attention was he mentioned that you could do simulation or Markov chains or calculus. So I figured I would try simulation first to come up with that probability. So what I did in Excel, first of all, I do use Excel for simple simulations, is I'm having Excel pick 2 random numbers from 1 to 6 and then format that as a 2-digit number. And then if that number is a 7, then don't do anything else. But if it's not a 7, then pick another number from 1 to 6 and another number from 1 to 6 and add them together and keep rolling the dice until you get a 7. Once you get a 7, nothing else happens. And I do that for 40 rolls, and I don't know if there's anything magic to the number 40, but I do that for 40 rolls, and then I'm looking to see within this set of rolls, did you get a 2 and a 3 and a 4 and a 5 and a 6, which would be the all small. And if that did not occur, then I'm just printing the word loser. And if it did occur, then I'm printing all small. And I did that through 10,000 columns. So I'm doing 10,000 simulations of that. And it looks like that's almost exactly Mike's number from the Wizard of Oz, 2.5%, 2.6%. But if I do another 10,000 simulations, that's 2.4%. So probably doing it 10,000 times is not enough. And so then I went over to a Java platform that I use from time to time, and I wrote a couple lines of code just to simulate this situation. And it simulates rolling the dice a number of times. And as soon as a 7 is rolled, you lose. But if you happen to roll the numbers 2, 3, 4, 5, and 6, that would be the all small. And so you would win. And so then if we do this, let's say 1,000 times, there we go. We got a 2 and a 3 and a 4 and a 5 and a 6. 2, 3, 4, 5, 6. So that was the all small. So then I decided I didn't want to keep printing out the result of each individual roll. And I didn't even want to print out whether I won or lost. I just wanted to keep track of whether I won or lost and then print out the probability. And instead of doing this 1,000 times, let's do it 1,000,000 times. And after doing it 1,000,000 times, this looks like it's turning out to be close to Mike's number from the Wizard of Oz, 026 something. And you see, even doing it 1,000,000 simulations, there's a little bit of variability. 0264, 0263, 0261, somewhere in that ballpark. So the next thing that he mentioned on the website was doing it using a Markov chain. And he said to do it for all small would require a 6x6 transition matrix. And I could not figure out how to make it happen with a 6x6 transition matrix. So I ended up with a 33x33 transition matrix. So what I'm calling state 1 is you haven't hit any of the numbers yet. Or you could have hit a 2 only or a 3 only, and so on. 2 and 3, 5 and 6. You could be in a situation where you've hit 3 of the numbers, where you've hit 4 of the numbers, where you've hit all 5 of the numbers, or you could be in a situation where you roll a 7. Now, no matter what state you're in, you can always get to another state. So, for example, if you're in state 1, which means none of the numbers have been hit, then you can get to state 33, which means you roll a 7. You can get to state 33 if you roll a 7, which happens 6 times out of 36. And you can stay in state 1 if you roll any of the big numbers, 12, 11, 10, 9, or 8, and there's 15 ways that can happen. You can transition to state 2, which means you've rolled a 2 only, if you've rolled a 2, but the probability of that happening is 1 out of 36, and so on. So for any state that we're currently in, we can figure out the probability of ending up at other states. Just to pick something a little bit more interesting to look at. As an example, if you're in state 17, which means we've rolled a 2, 3, and 4, you could stay in state 17 if you roll a 2, which there's one way of that happening, if you roll a 3, if you roll a 4, there's 3 ways of rolling a 4, or if you roll any of the big numbers. If any of those things happen, then you're still in state 17. Of course, if you roll a 7, which there's 6 ways that can happen, then you're in state 33. But you can go from state 17, which is a 2, 3, and 4, to state 27, which is a 2, 3, 4, and 5, if you roll a 5. So you can get from state 17 to state 27 if you roll a 5. And the probability of rolling a 5 is 4 out of 36. So it took a while to put all of the probabilities in this matrix. So there's my 33 by 33 transition matrix. And then I use the function mmult in Excel to multiply that matrix times itself. So this gives me the t squared matrix. And then I multiply it times itself again to get the t to the 4th matrix, and t to the 8th, and t to the 16th, and so on. And by the time I get that matrix 4096 power, you can see that all of the probabilities in that matrix, our transition matrix to the 4096 power, all of the probabilities are 0 except for these last 2 columns. And these last 2 columns representing state 32 and 33, which are the absorbing states. If you're in 32, if I go back to the original T, the original transition matrix, if you're in state 32, you stay in state 32. That means you've hit all the numbers. If you're in state 33, which means you've rolled a 7, then you have no chance of winning, so you stay in that state. So those are the 2 absorbing states. And one of the cool properties of this matrix when you do t to a really high power is this, that the ijth entry of t to the n, in general, the ijth entry of t to the n is the probability of starting in state I and ending in state j after n steps. But if you let n go to infinity, all those probabilities are 0 except for the absorbing states. So this probability here, so I'm on the first row, so that's starting in state 1. What is the probability that you end up in state 1 or state 2 or state 3? All those probabilities are 0. You will eventually move out of state 1. And the probability that you move to state 32, there's the number that Michael had on his webpage, and I pasted it over here. Let me copy and paste it over here to a little bit more decimal places. 26353, and on Michael's site he said, where is it at? 26354, but notice that's 353 with a 9. So very happy that using the transition matrix of a Markov chain ended up with the same probability. So about a 2.5% chance that we will end up in state 32, which means all of the small numbers have been hit. So anyways, I thought that was an interesting little math/statistics problem, and was able to do it via simulation and via Markov chains.